So here's our soapbox aspect. Notice in that red box you are relating what two things?
One mole of any gas.
I don't care about the number. You are relating what two things?
Substance and measurement.
So
Moles to liters. So it's a measurement relationship. Okay? Same substance. Officially the substance isn't listed there, but it's the same substance. Have we talked about a conversion that relates moles and liters already this semester?
Yeah,
Yes.
the molar mass.
Nope. Molar mass is going to relate.
I'm sorry, not the molar mass.
No, you're too late. Molar mass is going to relate. We'll come back to that. Molar mass is going to relate.
The molar mass
The
is
grams to moles. Joey saved you up front. It's okay. So mass to moles. Okay. What relates moles to liters? Allie's got it. Molarity. Okay. When was molarity used?
Did we use it last class?
We used it last class, yes. Why would we use it though? What was the point of using it? When was the value behind a molarity?
So if we did some type of feasible measurement that we,
A measurement for, yes?
for whatever we're trying to find.
Nope.
Oh, concentration.
It's a concentration. When do I need to know a concentration?
Aqueous.
Solutions, aqueous solutions. So that's when it becomes valuable. Okay, if we think to our lab experience, how many times have we worked with solutions? So when we did an experiment in lab, how many times did you have a liquid that you had to manipulate? Pretty much all of them. Okay, so liquids, very, very common. Molarity makes a lot of sense as a concentration is something that we need to work with. In those labs, how many did you manipulate a gas? Not produced a gas, not made a gas, said, ooh, look at that, it's a gas. How many times did you actually take a gas and do something with it? You really go back and look, it's not even seldom.
We didn't even do it.
You never did. You never work with a gas. Why?
Gases are unpredictable.
Gases are actually very predictable. They predictably go everywhere. Okay? We can't contain them easily. So gases as a thing are not the easiest substance to work with, which means you as students don't work with gases. Okay? So when we talked about our conversions, we talked about molarity first, and we didn't talk about this conversion. Because you guys have done a bunch of reading now through chapter 8 and 9, this conversion popped up in chapters 8 and 9. Okay, on how to do mole and volume conversions. And I told you not to read those sections at least first, and then we're now so far behind you've probably read them. Okay, so they talk about this gas conversion before molarity shows up, because molarity is chapter 13, I think. Okay, so we're addressing gases first. Got a big problem with that? Do we work with gases? No. So why are we making you work with a conversion that you'll never use? That's a good question. I think that's a big crock of something. Okay? So now let's take the next step behind this. Okay? So you rarely work with gases, but we've decided there's a conversion factor, so we're going to make you use the conversion factor in the lecture because we have one. Okay? That's our argument for this conversion factor. But maybe the conversion factor is useful and valuable. Okay? Because it's like, I don't know, universally accepted. Well, it's not universally accepted. It's only accepted for gases. Okay? Okay. We'll pause and be like, okay, it's true for gases all times. No, we've got in parentheses an exception. It's only true when at STP. Okay? So when I told you to memorize things, the things I told you to memorize were true when? Always, without any exceptions. Okay? Because that's something we should commit to memory. Okay? If there's exceptions, we're going to have to figure out what all those exceptions are. So I've got a big problem with this because there's exceptions. Okay? Now the next stage. Maybe when at STP, maybe that STP makes sense because we're always at STP. Well, what is STP? Standard temperature and pressure. Does temperature fluctuate?
Yes.
quite significantly. So what are the odds we'll ever be at a single temperature? Okay, rare to none. So we're using a conversion factor for a substance that we don't work with already under conditions that probably aren't going to stay constant. This is becoming more and more a challenging and stupid conversion factor to make you memorize. Okay, add to that pressure. Is pressure constant? Same deal. This is only valid when these two things are constant and those two things are rarely constant. That's problematic. Okay? Now let's look at what those actual things are. Standard temperature, okay? Let's just, because we are in air-conditioned rooms, the temperature is relatively constant within that room. What is standard temperature? Room temperature would be an awesome guess. Okay, the problem with room temperature? What is room temperature? Okay, you'd have to be very specific about that to actually nail it down perfectly. It's usually between 20 and 25 degrees Celsius. Okay, I can't do the math, but probably around 70 to 75 Fahrenheit. Okay, somewhere in that range. Okay, so maybe that's relatively constant. Is that standard temperature? No. What is standard temperature? 0 degrees Celsius. When was the last time you were at 0 degrees Celsius?
In the Midwest.
Okay, we could argue in the Midwest. Okay, maybe if you went up to Flagstaff this winter, you were at 0 degrees Celsius, and even then, oh no, that should be true, yeah.
That's that right
Okay,
now.
it's actually there right now?
Yeah, yesterday it was 25 degrees at night.
Wow, so there you go. So in Flagstaff, we're at 0 degrees Celsius. Are we going to be at 0 degrees Celsius here? No. To do that, we'd have to be in a freezer, literally a freezer, to make that condition valid. Okay? That's a pretty dumb conversion factor. What is standard pressure?
1 atmosphere.
1 atmosphere. And again, pressure is relatively constant, but that's 1 atmosphere where? Where on the planet are we at 1 atmosphere?
Everywhere.
Nope. Sea level. As soon as we change altitude, we're no longer at 1 atmosphere, and it changes. Okay? Again, that change is relatively small, okay? But it's significant. So we're having you memorize a conversion factor for a substance you don't use, okay? At temperatures you'll never be at pressures or temperatures and pressures that are never constant, at temperatures that you won't be at, and at pressures you probably won't be at. What is the point of making you memorize this conversion factor?
Do not know.
To make you do more conversions.
Why?
That's it. I completely agree. Why? Okay? I think it's completely and utterly useless, okay? And we should not be making you do it. That said, ta-da! You are responsible for knowing that conversion factor and using it. It allows us to relate moles into liters. You could make the argument, the reason we're making you do it is that it's allowing us to relate moles to a different measurement system. Okay, liters. Okay, which we already had for liquids or solutions. This is now a new phase, so we have to show a new measurement. Okay, so that's why we have to bring in the phase argument. We also already created a mole conversion for solids. What was our mole conversion for solids? Nope. How would you measure a solid? How do you measure a solid? I ask you to go into the lab and measure a solid. What are you going to measure? You're going to weigh it on the scale. You're going to take a mass of it. So what is our conversion between the moles and the mass? Joey and James should be all over this. Molar mass. Okay? So Kira came in, molar mass. Okay? So what we're trying to do is address and tie how moles can be related to a variety of different measurement systems and a variety of different phases. Okay? So that's kind of the point behind it. So there's some utility behind that because we can show that there are different ways to relate it. Okay? Unfortunately, that relationship we're picking is something that we never work with, and we probably won't ever do an experiment at those conditions. Okay? And if we aren't doing an experiment at those conditions, that doesn't work. Which adds in the next thing, standard. What does standard mean to you?
Whatever I believe in.
What's that?
Whatever I believe in, like me as a person, that's what my standard base is at.
Okay, so your standard belief, okay, that could work for your personal, okay, and I would argue that's probably not standard.
It's a social norm.
A social norm, a social convention, okay, which is great because we all have the exact same social norms and social conventions. Well, but we're scientists, so yes, we have the same social convention between all scientists. So when you talk to a chemist and they say standard temperature, they're 0 degrees Celsius. My wife and I were working on her instrument because she's an engineer and she's making solar cells. They use gases and they're trying to figure out what was going on with their system. They couldn't figure out why the gases were flowing at weird rates. They were getting weird results. So she went through and tried to run some calculations. Those calculations required her to use an expression that involved standard temperature and pressure, okay, behind the underlying assumptions. Kept getting things that made no sense. What the instrument was spitting out and what we were calculating made no sense. She ran it by me and said, you know more of the physics behind this. Explain to me why this isn't matching. Couldn't figure it out. Nothing lined up. Nothing lined up. We're like, it's got to be something wrong with the instrument.
Turns out it was my fault.
Turns out it wasn't Greg's fault necessarily. Okay. The engineer that designed the system said what was standard temperature. Room temperature. So everything that they based off the measurements, the flow rates, all of those results came from a different standard. Socio-cultural norms aren't very standard. Okay? So even within science, if you go from one scientific field to another, standard temperature and pressure can change. This can drastically F with that conversion factor. All the more reason we should not be forcing you to memorize it. What we should be doing is providing the context on where that comes from, which we'll see in a little bit. All right. That was almost 5 minutes, just 15.
It's actually pretty impressive. That's one of the fastest ways to press.
I'm not sure if that's a good thing or a bad thing. Okay. Gas force. Okay, so there's this force that gases exert is our pressure. Okay. So let's use that conversion factor. Okay, what am I solving for? What do I want?
Liters.
Okay, liters is half right. What do I want?
Liters needed to hold.
Liters of what?
Liters of hydrogen.
Liters of hydrogen. Hydrogen, what? Gas. Okay, this is important. When we write out what we want, it is the measurement and the substance. Okay? I believe I've said measurement and substance now every lecture. We should not be at the stage now where you're like, well, I'm just going to specify just the measurement. We aren't there. If you're only doing that or only doing the substance, you will get questions wrong. What you're now relying on is that you've memorized how to do all of these calculations. Okay? You must specify both. Yes?
Would we need to add in gas?
The gas is going to become relevant here in a second.
Oh,
Okay? Technically, no. We don't have to reference it. The reason it's going to become relevant is when we deal with the rest of this. Okay? So that's what do I want? What do I have?
2 grams of hydrogen gas.
Okay? I would argue the 2 is irrelevant. What do we have? Grams of hydrogen gas. Do I have a number to associate with that? Yes. 2. Okay? What do I want? Liters of hydrogen. What do I have? Grams of hydrogen. Are they the same thing? No. So what has to happen? I have to do a conversion. What did I want? No? Fix it?
Liters of hydrogen gas.
Liters of hydrogen gas. Okay, what do I have? Grams of hydrogen. Does that conversion factor exist? Grams to liters. No. Okay, which means I'm going to have to pick something else. So which do I want to look at? Liters or grams? Grams. What can I convert grams to?
Moles.
Okay, I could convert grams to moles. Where do I find the conversion factor to relate grams to moles?
From memory.
What's the number?
22.4.
No.
Oh.
Okay.
Oh.
It's the periodic table. Hydrogen has a mass of 1.01 grams per mole. If there's 2 hydrogens, my mass is 2.02 grams, 1 mole. Okay, what do I want?
Liters of hydrogen gas.
What do I have?
Right now you have moles of hydrogen.
Good. Okay. What do we have has now changed because we've done a calculation. What we have now is moles of hydrogen gas. What did I want? On top, what do I have on the bottom? Does that conversion factor exist? Now, Zach?
Yes.
Yes, I've got this one, and this one
22.4.
is 22.4 what?
Liters per 1 mole.
22.4 liters is 1 mole. Where did we get that? From that expression that we had on the last slide. Okay. On the test, you don't have the slide. Where do we get that? Memory. Why from your memory and not the front of the exam? Because I told you you have to memorize it. So this has to be a memory thing. Now what happens? What do I want? Liters of hydrogen gas. What do I have? Liters of hydrogen gas. Because the units are the same, now I can run the calculation. Okay? Zeke had asked an important question. Did I have to specify that gas? When is this conversion factor that you've memorized valid? When you're dealing with a gas. Was it important to specify that we had a gas? Okay. So it's not critical to write here, except what you're doing is acknowledging that that conversion factor is now valid because we're at a gas. Does that make sense? Okay. So all we're doing is identifying that key information that allows me to use that conversion factor. If I didn't have that key information, then it becomes questionable on whether or not I should be allowed to use that conversion factor, which might be why Kira was about to ask something.
I don't think it is the same thing, but I don't know if this is just me, but the question like trips me out because it says how many liters are needed to hold 2 grams of hydrogen gas, and so I feel like it doesn't specify what the liters are because it just says like how many liters, and then it just says 2 grams of hydrogen gas.
So what would be in those liters?
I guess, I mean, it makes sense now, but it like confused me.
And I'm not disagreeing with the confusion aspect behind it. This is one of the things that we do have to reason through. This we can blame sort of Greg and sort of chemists. We can blame Greg because it's the English language and chemists because maybe we should learn English a little bit better to make our questions less confusing. That said, what happens when we get out into the real world? I have 2 grams of hydrogen gas. How the hell am I holding it? What do gases do? They go everywhere. How did I measure that 2 grams of hydrogen gas? Okay. If it just goes everywhere, I'm not holding it. So how am I holding it? I would need a container to hold that thing. How many liters should that container be to hold that gas?
This is making more sense.
Okay? And so a lot of the questions that get asked have this kind of implied lab concept behind it, which isn't necessarily obvious in a lecture because there's no lab component right here. Okay? The lab component is outside, which brings in the extra issue. We're not ever working with a gas. If we don't work with a gas, how do we get that kind of physical reality behind it? Okay? So that isn't where I thought you were going to go. Okay? So we can kind of go back after Zeke's thing. Did I have to say gas? No, but it was important to acknowledge that I'm allowed to use this conversion factor because it is a gas. Because that's when that conversion factor is true. Is that the only thing that's a consideration for this conversion factor? Is it true for all gases at all times?
No, it's standard.
Okay. It must be a gas, and it must be at standard temperature and pressure. Okay. So the question clearly says that we're at standard temperature.
No.
It clearly says we're at standard pressure?
No.
No.
You assume.
Okay. We assumed. Okay. Why did we make that assumption?
Because it doesn't say otherwise.
It doesn't say otherwise, and at this stage, as far as both in the textbook and in the lecture, we haven't provided a context for how else to do it if we weren't at that. Okay? Making assumptions is a horrible thing to go through and do. Sometimes we have to do it in the situation that we're in. Ultimately, it's a crap question. The question should have said, how many liters are needed to hold 2.0 grams of hydrogen gas at standard temperature and pressure? Okay? Or at 0 degrees Celsius and 1 atmosphere. Okay? We're now converting that STP into what the actual meaning of ST and SP are. You're responsible for all of those contexts.
If we see a question like this on a test or something, or is it appropriate to add that in as part of your answer to provide the context, assuming standard temperature and pressure this if the context isn't given the other way?
And that's a really important question. If you now see this on an exam, what should you go through to do? In a show your work, you could be like, I think this said STP, okay? Or it was implying STP. Because what are you getting graded for in a show your work? Your work, which is ultimately the thought process behind how you solved it. If you've identified what that thought process is, now it becomes harder for whoever's grading to be like, well, no, you didn't do what I asked you to do. Well, your question sucked. I've showed you the underlying assumption behind my calculation. Now I've run the calculation as is. Okay? What if it's multiple choice? Are you getting graded for your work? No, you're getting graded for your answer. Okay? So now the question becomes, well, do I need to specify that it's at STP? Is there something that I could be looking for to help me trigger that they're assuming STP? That is the ultimate end goal that I want you to get to, absolutely, which may irritate the crap out of future instructors, which is ultimately their problem because they wrote a crap question and you should draw attention to their failures. Okay? For better or worse. Okay? In this class, absolutely. I want you to raise your hand and be like, did you mean to say at STP? Okay? Or like, I think there's some information missing.
Like in the middle of the test.
In the middle of the test, you should absolutely be making that statement and asking. What you've done is proven that you understand the content. If anything, when I go back to grade, now I'm like, well, damn, they actually called me out on my failures. I need to be making concessions and maybe adding more points back because at least someone in the class was paying attention to what I said. Okay, so that can benefit everybody in the class by you challenging the validity of a question. Okay, during the exam, or even after the exam too. Okay? It should really happen during the exam in most circumstances because if you do it after the exam, you've now passed the point of no return. You're relying on the kindness of the instructor to backtrack. Some instructors, as we had earlier conversations about today, don't like backtracking on it, okay, and see it as a power dynamic. Other instructors don't really care, okay, and say, yep, we're all fallible, I screwed up. Let me fix it. Okay? That said, I try to pay attention to this. Okay? And if this question showed up on the test, guess what one of your answer choices might show up to be. Okay? And so this is the point on deciding, should we be making that assumption or not? Look at your answer choices. If one of your answer choices makes the assumption, then you could be like, yeah, I need to make the assumption. What if one of your answer choices was there? You shouldn't be assuming. Okay? That question is now pushing at you. Do you acknowledge that you had to make the assumption? Okay? You should not be making assumptions, period. Okay? And if you see that question or that answer choice not possible, okay, a lot of people go through and acknowledge will say, well, that's just a fake answer, that's not true. That is a horrible statement to make. Anybody that's built a proper exam has that as a valid answer for a particular reason. In this case, that particular reason would be we didn't say at STP, we can't solve this.
Other
Right?
people might go back and say, because it's a weird answer, like I automatically know it's correct, that's the one.
Right?
Don't do
So
that either.
we have to be very careful with how we approach these questions. Okay? Particularly in this case, we've talked through this, so you will likely see a not possible with the given information. I might also add at STP to the question, which then means the not possible is not a valid answer. It is possible. Okay? So you have to be thinking critically about the information you have. You should not be making assumptions about questions. Okay? If you don't want to ask an instructor because you're in a groove on the exam, skip the question, go through. Okay? But at least flag it so that at some point, at the end of the exam, you can be like, did you mean to provide this or not? You've at least now put it in the instructor's head that they may have goofed. Okay? That can help your case further on down the road. Most of your education and life is about building the best defensible position for yourself to advance through.
And causing doubt in those in authority over you.
Yeah.
Seriously, actually, yeah.
The more you can cause somebody else to be like, oh, yeah, I might have screwed that up, the more likely you can advance over them. Okay? Is that a hand?
Yeah. Are we learning anything else other than STP?
Yes. Not yet, but yes. Is there another question about what's up here? Okay. So that is our basic pattern. You're required to have this conversion factor memorized. I'm irritated that you have to memorize it, but you do. Okay. You also have to realize that it is at a gas and it must be at STP, or for gases only and at STP. For that conversion factor to be true. 1 mole equals 22.4 liters of any gas at STP. Okay? So, if we tried this, how many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? What do I want? Liters of hydrogen. And in particular, liters of hydrogen.
Gas.
How do you know it's a gas?
Because hydrogen in its natural form is a gas.
Acceptable. What's another reason? If we look at the equation, it says G. G means gas. Okay? So yes, we're looking at a gas. As soon as we get the idea that maybe we're looking at a gas, we might want to just immediately assume that this 22.4 liters equals 1 mole is going to show up somewhere. Where and why and when, I don't know. So I wouldn't immediately start to use it, but acknowledging that you're at a gas, that conversion factor is potentially going to become useful, could help out. Man,
And
spitting
writing it down like that becomes a visual trigger as you're solving the problem, so that you remember to check before
Okay.
you get lost in the numbers or whatever.
Notice as well, gas, 22.4 liters is 1 mole. When? At STP. Was it stated?
No.
No. Should we assume?
No.
No. So what are you going to do?
Mike, is this at STP?
Yes, this is at STP.
And if I were getting in the habit of writing that, I would put STP question mark under every time I wrote that personally. If I'm like, I need to make sure, and it's meant to like help me remember things. I'm not sure if it applies, but yeah, that's what.
Okay. What am I given? Okay? Grams of aluminum metal. Where should I place the grams of aluminum metal as a given piece of information? Numerator or denominator? Why in the numerator?
Never mind. That's not what we're finishing.
Okay? So one argument would be, well, grams isn't what I want for a measurement. Aluminum isn't what I want for a substance. Okay? So you might be like, well, I have no idea where I would place that. In the absence of more information, place it in the numerator.
You can just do it at
Okay?
level 1.
Because what we could go through and do is run the calculation and be like, well, crap, the units didn't work. Why did the units not work? We made the assumption of placing that in the numerator. Our assumption was wrong. We now have evidence that it is wrong. So what could we do? Flip it, put it into the denominator, and then try and run our conversion and see if that fixed it. Okay? This is why the units are so powerful. Okay? This will be over 1. What is the number associated with this? Oops. 0.165 grams of aluminum. Okay? What did I want?
You want liters of hydrogen.
Liters of hydrogen. What do I have? Grams of aluminum. Is any part of those units the same? No, which means minimally I have 2 conversions. What are those 2 conversions? Substance to substance conversion and measurement to measurement conversion. Minimally, both of those have to happen. I could have more, okay, but minimally I need those 2 things to happen. Okay? This is where I would argue what you should do is focus on the more important one. The more important one to me is always the substance. Okay? Measurements we can convert up to yin-yang. This is why you spent 18 years of your life learning measurement conversions and not talking about substance conversions. Okay? So the substance conversion is the harder one. Let's get that one out of the way first. Okay? What do I want for my substance?
You want liters of hydrogen.
For my substance. Hydrogen gas. What do I have? Aluminum. Where do I find a substance conversion? From a chemical equation. And in particular, what kind of chemical equation?
Balance.
A balanced chemical equation. Am I given a chemical equation? Is it a balanced chemical equation? No. So for me to go through and do anything with this conversion factor, I'm going to need a balanced chemical equation. Okay? So let's real quickly balance it. 3. I think I did that right. Did it kind of sporadically because somebody else already did it for me. Okay? So we now have a balanced chemical equation. Before we drop those numbers into our conversion factor, we have to make sure our units for our conversion factor are correct. What are the units from a balanced chemical equation? Okay. From this balanced chemical equation, I would say there are 2 possible units, as a hint. Usually we could pull in a third, but from this chemical equation, there's only 2. If I give you 2 molecules of aluminum, how much aluminum chloride can you make? 2. 2 what? What's the measurement? Aluminum chloride's the substance. What's the measurement? Okay. If we stick with Ali's reference, compounds. Okay. I'm still having a hard time with that one. Sorry, I keep calling them molecules. Okay. So one of our units, our measurement units, it's a little bit of a weird one, would be molecules or compounds. Compounds from the chemical equation. Why do we not use molecules or compounds as a measurement unit typically? If I go into the lab and have you measure out a compound of aluminum chloride, how much is that going to weigh? So tiny we need a $19 million balance. We don't have that budget. We barely have the budget. I'm planning on donating to the school $2,000 to buy an instrument. We don't have $19 million, okay, for a single balance. Not going to happen, okay? So what is another measurement unit that we can get out of the chemical equation that allows us to scale up to a decent mass? Moles. So when we go through and look at that conversion factor, this is moles of hydrogen and moles of aluminum. Note that because we're changing the substance, we cannot change the measurement. The measurement must stay the same. What are the numbers associated with those? The 3 moles of hydrogen, because there's a 3 in front of the hydrogen. What's in front of our aluminum? 2. Okay. What do we want? Liters of hydrogen. What do we have?
Moles of hydrogen gas and moles of aluminum.
We have moles of hydrogen gas, we have moles of aluminum, and we have grams of aluminum. None of those units canceled.
We're farther away.
Okay? We're further away from our goal, but we've at least established that we know how to do that conversion. That's a really important thing to add in here. Okay? So, what do I want? Because now we've got multiple things that we could go through and do. Okay? We could keep our singular focus. I want liters of hydrogen. Okay? What do I have? I got a ton of stuff. Which of those ton of things that I have would be most useful to relate to liters of hydrogen? So let's put it this way. If you don't know, guess. I'm going to do grams of aluminum. What happened to the measurement unit? It changed. What happened to the substance unit? It changed. Does that conversion factor exist? No. So that sucked as a choice. Taylin, go for it.
I have a question. So because we can do the 1 mole of any gas equals 22.4 liters, can we use that right there? Or does it be...
So I said grams of aluminum didn't work as a substance relationship, so I'm going to use what else I have. What else do I have? Moles of hydrogen. Is there a conversion factor between the moles of hydrogen and the liters of hydrogen?
Yeah.
Okay. What is that conversion factor?
22.4
1 mole was 22.4 liters. Where did we get that?
from the equation.
We were supposed to memorize that. And we memorized that for gases at STP. Is that what we had?
No, we assume.
Remember, no, because you raised your hand.
Oh.
Raised your hand. You raised your hand and asked, and I said, yes, it's at STP. So we did know that. Okay, so that conversion factor is valid. So can we just bring that in? I don't like the phrasing of your question, okay, but yes, we are bringing that in. The question becomes is why are we bringing it in? We're bringing it in because that's what we needed to do to deal with those units. Does that make sense? So it's not a just bring in. We have a really solid explanation for why it's coming in. Yes, Krista.
Does it matter that it says 3 moles?
Does what matter? Where does it say 3 moles?
3 moles of hydrogen.
Where did that 3 come from? From the chemical equation. So you're saying, shouldn't that 3 be here?
Yeah.
Okay, where did this 1 come from? From the memory of this expression.
Yeah.
Is this expression have anything to do with the balanced chemical equation? Are they the same source of information? No, they are independent pieces of information. I could care less that that says 3. For the same reason I could care less that that says 0.165 grams of aluminum. Okay? Just because the unit is the same doesn't mean the number is the same. This becomes the value of this process. I'm relating those units. Where do I find the relationship between those units? Okay? The chemical equation doesn't tell me the relationship between those 2 units. That's why I can't bring that 3 in.
Okay.
Okay? Okay? So, what do I want? Liters of hydrogen gas. What do I have? Liters of hydrogen gas. And
Moles of aluminum and
moles of aluminum and grams of aluminum. So do I have my answer? No. So what do I need to do? Okay. What do I want? Well, at this point, what do I want was liters of hydrogen gas. So actually, my what do I want is actually what do I want to get rid of? I don't want grams of aluminum. So, grams of aluminum. Am I given just the grams of aluminum?
Yes.
Yes. Did I already use it?
Yes.
Yes. So should I be putting that number in there? No. Okay, so I need to relate the grams of aluminum to something. Why do I want to relate it to moles of aluminum? Was there something else that I wanted to get rid of? Yes. Okay. Is there a conversion factor that relates the grams of a substance to the moles of a substance? Yes. Where's that found? The periodic table. And that says,
35.
try again, 26.98 grams was 1 mole. It's okay. Grams of aluminum cancels. Moles of aluminum cancel. What do I want? Liters of hydrogen. What do I have? Liters of hydrogen. Which means now I can punch into the calculator my whole sequence of calculations. Okay? If you need help with punching into the calculator, that is quite all right. You should talk to me after class. Okay? We're not explicitly teaching you how to use a calculator in this course. Okay? At least in the lecture. Okay? So that is how we go through and solve that process. Each time, what do I want? What do I have? What do I want? What do I have? What do I do not want? Let me fix that. Okay? And attempt to align those conversion factors. Okay? Realizing within each of those sections, it's a given, it's its own contained unit. And I forgot this one. Where did we get this one? The 0.165 grams of aluminum. This was given. So when you write down your work, did you write down just this calculation here, or did you write down that this was given, that this was the balanced chemical equation, that this was memorized and that was from the periodic table? You're writing all that? Good. Every time you solve a question from here until Thursday, and I was going to say you could stop. You can't stop. You need to be specifying where you're finding that information. Okay? All the way through. Yes. What do you mean we write it in different ways?
Like, it's all the same information, but, like, it's, like, different. Like, 'cause you can't, like, cross out as you go down, if that makes sense.
Okay, so what I think you're referencing here is that the order in which we've provided that information has changed. It's not always the same. And a lot of that comes from what we see allowing us to move forward. Okay? When you get in your car and back up, do you do the exact same thing every time? Okay, almost? Really? So when you see someone standing behind your car, you're like, back it up.
Oh,
I got it.
I thought you meant, like, before I back up. Like, I do the same, I turn on my car, I look at
And even then?
look at the thing.
Okay, so you turn on your car. If you're carrying 4 hot coffees, you take the 4 hot coffees, you walk in, you let go of one of them so you can put the key in.
Well, you didn't specify that every time would be different.
I said every time. So every time comes down to what you see at each of those cases. Sometimes you see the same thing, so you follow the same patterns. Sometimes you see something different. Okay? And that is one of the things that's challenging within these. Okay? When we moved through this, what we started with is grams of aluminum, liters of hydrogen. There were 2 different conversions that we had to do. Okay? What I told you is what I see and I think is going to be the best path is saying that substance conversion needs to happen first. Okay? If you decide to try and do the measurement conversion first, okay, what you'll find is you'll hit a lockup point where you're like, well, what do I convert that measurement into? Okay? If you address the substance conversion first, you can find an easier path through, okay? And there's less questions at each of those stages, okay? But even then, after we did that, okay, and we were here, and we had all that information, I asked, what what did we have? Okay? Or what did we want and what do we have? Okay, we had liters of hydrogen and then we had all of those units. I said, okay, what did you want to do? I think it was Kira. I don't know. Somebody said liters of hydrogen. So we stuck with what we had or what we wanted and just tried to work and hoped for the best. Okay? We didn't have to do that one first. We could have done that one first. Okay? And a lot of that just comes from what you see. Sometimes if you've done enough questions, you'll find that you always do the exact same thing. Okay? Doing the exact same thing isn't necessarily a bad thing, okay? As long as you're doing it right. Okay? And as long as you're acknowledging that it doesn't have to change. Okay? What I want you to give you, though, is the flexibility to be able to jump to any different direction. And yes, that is more challenging for both you and me, because now I'm not saying follow me lockstep. I'm saying follow with what you see. Okay? And I'm working through with what we've got.
And you went into more detail, like you covered that substantially, I think, on Thursday or Tuesday. So going back, if that's the struggle at all, going back to those PowerPoints from Thursday or Tuesday would be a good idea.
Yeah.
For the 3 and the 2 moles, would those just be one sig fig or infinite?
Good question. Sig figs off of those. Those are now infinite from our balanced chemical equation. Okay? The best way to kind of address that is, could that be 3.1? If you made this 2.1, would that have balanced? No, so that would have needed to be 2.1. Right. Okay? Which then means how many chlorines would you have?
2.1 times
2.1 times 3. Okay? Out on top of that, remember, the units that could come from this, we could get all the way down to molecule. Can I have 0.1 of a molecule? No. Okay? I can have 0.1 of a mole, but that's a separate issue. Our balanced chemical equation ultimately boils all the way down to molecules. We're just scaling it up to moles. So we have to maintain that same kind of significant figure value. So from our balanced chemical equation, those are infinite sig figs. Damn, that was deep. Okay? Cool. So let's stop dealing with, I forgot about all this. So Y units is just kind of a secondary thing. If we look at these 2 questions, how many moles and 9 whatever numbers, okay? If we look at kind of the standard method that you were kind of referencing, it's always changing. Why can't you just be constant? If I become constant, what I'm doing is now telling you a formula to memorize. So to answer those 2 questions, I have 1 formula, 2 formulas, and I have to know where to find that information. If we go according to the process that I'm telling you, it's just where do I find that information? The rest of it is just the process. Okay? Well, what if we switch to now liters of calcium? New formula, okay, with only 1 extra piece of information. Okay? If we teach you formulas, you have to memorize each of those formulas, each of those contexts, each of those processes. Your standard method of just memorization explodes with the amount of things you have to memorize. If we just go through with the process, it's now just adding 1 more piece of where do I find that information. Okay? So it becomes a simpler thing to scaffold. All I have to know is where to find it. Okay? And for those of you that might think, well, dang, this is kind of a hard concept. Okay? Mike makes it sound so easy, it's not that big a deal. There are people in general chemistry right now that we're struggling with because they don't understand the process. All they've learned is a calculation of a formula, and so as soon as the question changes a little bit of context, dead in the water, have no idea how to solve it. Because all they've memorized is a formula, not the process behind it. Okay? Your questions will constantly change, both through chemistry and through life. We need a process that is robust enough to adapt to those changes. That's the point of dimensional analysis. Okay? That was another soapbox. Let's get away from the soapbox. Let's stop doing conversions. Atmospheric pressure. Pressure is the result of our gases pushing on something. Okay? If we take a look at atmospheric pressure, somebody was playing around with a glass tube. You've probably done it. Take a straw, right? Fill it up with liquid, and you put your finger on it. Okay? And you put it in something, and you might see the layer of the liquid drop a little bit or fluctuate. Okay? Why is it fluctuating? Okay? if I look at this, shouldn't the liquid all just fall out of that? What does gravity do to liquids? It pulls them down. Why is the liquid staying up there?
The air that's in there.
Something must be pushing it up to keep it up there. Well, what's pushing it up? Okay. So one of the initial assumptions would then be magic. This is why scientists were hung for witches. Okay? Because some invisible thing that I can't see is doing something. What is that invisible thing? It's the atmosphere. The atmosphere is pushing down on the liquid at the bottom. For the liquid in the tube to come down, what must happen to the liquid in the bottom? It must come up to account for that extra volume of liquid. If the atmosphere is pushing down on it, the liquid can't drop. Okay? So somebody was playing around with this and noticed, hey, look, I can make liquids hover. Okay? And then they got bored with it, walked away, left it alone, came back a couple days later and was like, what the hell? The liquid moved. Why did it move?
Pressure switches.
The pressure changed. Atmospheric pressure changed. They're like, oh, cool. So it goes up and down kind of randomly throughout the day, weeks. That's fun. Then they noticed that it dropped, but then it rained. Well, damn, if it drops low enough, I can predict that it rains. So now I can be an extra cool wizard. Because I can just look at the level in my liquid and say the liquid dropped, and I go out, it's going to rain. And it was like, it's a bright sunny day. It's going to rain. 24 hours, rain comes down. Give me all your money because I will destroy you because I can predict the weather. Okay? I control the weather. All it's coming back to is making simple observations about atmospheric pressure. Okay? We may not have acknowledged that that's where it was coming from at first, but then somebody smart enough was like, you're just being a jackhole. You're just reading a stupid bar. I can do that too. And then that original person gets, killed for stealing money. Okay, or praised for stealing money. If I don't know, I want to jump on that soapbox. Praised for stealing money because they did a great capitalistic thing. Take a step back. Atmospheric pressure is a measure of that gas pushing on us from around. Okay? If we look at this tube, some things or some liquids do better than others at predicting that atmospheric pressure. Because some liquids, if I leave them exposed like this, do what? They evaporate. Well, if the gas is no longer, or there's no liquid there, what happens to the liquid in the tube? It's going to fall. Is it falling because atmospheric pressure changed? No, it's falling because there's less liquid at the bottom to hold it up. Okay? So we would have to kind of experiment around with differing liquids to predict that. What we're referencing there for our liquids is something known as the vapor pressure constant. Okay? All liquids have a vapor pressure. So if I have a liquid and I'm talking about its vapor pressure, well, what was pressure a measure of?
Gas.
Forces for gases. But I'm talking about a liquid. What does the liquid naturally do? It goes into the gas state. Its ability to transition into the gas state is known as the vapor pressure. So if I have a very high vapor pressure for the liquid, what am I saying? There's a lot in the gas state. Right? If I'm trying to measure atmospheric pressure, do I want a liquid with a high vapor pressure? If it's a high vapor pressure, where's my liquid? It's in the gas. So all of this liquid with a high vapor pressure, I have lots of gas. So all of this liquid down here goes where? To the gas state. If it's in the gas state, is there anything holding the liquid up in the tube? Nope. So what happens? It falls down. So for measuring that atmospheric pressure, I want a liquid that has what for a vapor pressure? If it's high, what happens to the liquid in the bottom? It goes away, which means what happens to the liquid in the tube? It drops. And it's dropping not because of atmospheric pressure, but there's no liquid there to hold it up. So what do I want for my vapor pressure? An insanely low one, so that it always stays a liquid. Okay? That way, when the liquid in the tube changes height, it's only changing because of the atmosphere pushing against it. There's only a few substances that have very low vapor pressures. Okay? The most common one is, okay, I hear a lot of people saying water. So when I leave a cup of water out on the counter, okay, if I put a cup of water here and then we walked away and came back next week with it open, would you still see the water in there?
It'll probably be through the bottom of the cup.
It's not acid.
I've seen it where it just
Okay.
or spread.
So if I left it there till next week, you say it's still there. How about in 2 weeks?
Yeah, there's nothing changing.
Nothing's changing.
It's not gonna evaporate.
Okay? This is the desert, right? Okay? How many of you use a dryer?
Blow dryer?
No. We can even reference a blow dryer. That works. Like a dryer for your clothes or a blow dryer for your hair.
Okay.
Well, then my hands that way I go on.
Yeah, everybody's like, oh, I use that. Why are you using that?
Dry your clothes, get the water out.
Okay? What happens if you just left your wet clothes hanging on a line?
It will dry.
It will dry. Why is it drying?
Just the water evaporates.
The water's evaporating. It's going from a liquid to a gas. There is a huge argument for the place where we live that you should stop spending money on a dryer. You're literally paying both a company to build an instrument for you and now paying a company to power that instrument to remove water from your clothes that if you just hung them up for an hour, the same thing happens. Right? In the summer, it's actually faster to hang your clothes than to run them in the dryer. You might be, that's not true. I know it's true because I hate freaking using the dryer because I'm a cheap jerk and I don't want to pay somebody else to do something that I can get for free. Okay? And it works amazingly.
Back to the whole thing, is that where like we get the partial thing, what goes up must come down?
No.
Oh, okay.
So what liquid do we typically see in these? Say, and even thermometers, because it's ultimately measuring the same process. Mercury. Mercury is a standard substance for this because the vapor pressure for mercury is next to nothing. Okay? Water is about 100 times higher vapor pressure. Okay? So mercury does not transition to the gas phase easily, which means it's great for measuring atmospheric pressure. There are other substances that can do the same thing, but they're usually a little bit more man-made. Okay? Here we've got it right out of the gate with an element that's relatively easy to isolate. Okay, what becomes the problem with mercury? It's highly toxic. Okay, so that's why we started to shift away from it. Okay, but mercury has a next to nothing vapor pressure. Okay? As we increase the temperature, what happens to the amount of gas? I got a pot of water and I increase it to 100 degrees Celsius. What happens to the amount of gas? It increases. What's going to happen to the vapor pressure? Vapor pressure is just a measure of how much gas is there. So if I increase the temperature, what happens to the vapor pressure? It also increases. Okay? We'll talk about that later. Okay, units of pressure. The standard one that I want you to remember is 1 atmosphere. Standard pressure is 1 atmosphere. Okay, notice there's a multitude of conversion or units for pressure. That's what this table is telling us. 1 atmosphere is equal to 29.9 inches of mercury, which is equal to 76 centimeters of mercury. Why do we have so many freaking measurements for pressure?
That's true, because when we get like atmospheres and we have PSI for like tires.
PSI, kilopascals. Why might we have so many different measurements? Is this an easy thing to observe?
No.
Probably not.
When you walk outside, do you feel the air?
Yes.
Is this an easy thing to observe?
Yes.
Yes, this is so insanely easy. Guess what? Hundreds of people have made the observation, which then means
Yeah.
hundreds of different unit systems to represent it. Okay? And because each of those unit systems or those discoveries, if you will, were made in slightly different contexts, guess what happens? That unit wins out for that context. For instance, PSI. Where do we see PSI?
Tires.
In tires. Okay? Because it's the pounds of air pushing outwards on the tire. Okay, it is that force. That's why PSI wins out. Okay, it's also pounds per square inch, which is the American system. Okay, so we create different unit systems. With different unit systems, what then must happen? They must all connect through what? Conversions, which would mean more conversion factors for you to go through and learn and manipulate and use. How many of you want to use those? Okay, how many of you want to use those? None of you. Okay, I agree. Let's not do it. Variables that affect gas pressure. Okay, what's going to change the amount of pressure that we feel from the gas? Temperature. Okay, so if we look at that relationship, what happens when I increase the temperature? What happens to pressure?
It goes up.
It goes up. Okay, so pressure is directly proportional to temperature. What else affects our pressure? No.
Right?
What's that?
It has something to do with when it rains, but I don't know.
Let's see
why
that.
that-
I'm not quite sure what that's referencing. We've got temperature. What's holding our gas? What does pressure measure? What is pressure?
The liquid inside the.
That's vapor pressure. And that's also not quite right. What does pressure measure? The force from what? From gases. Okay? So if we're talking about our pressure, how do we contain a gas? In a container. How would we measure, say, something about that container? The volume. Okay? Are pressure and volume going to be related to each other?
Yes.
In some way.
In some way. What is that some way? If I take a container, okay, with some amount of pressure or some gas in there, it's got a pressure on it, right? What happens if I shrink that container?
Pressure goes up.
The pressure goes up. If I decrease the volume, pressure increases. What does that mean? Pressure is indirectly, or not indirectly, inversely related to volume. Okay? What else could change or affect my pressure? Sort of. Okay. Mass. How can I get you to not say mass? Don't say mass, but yes.
You just say, don't say math.
The substance isn't a bad idea, changing the substance, except one of our assumptions for gases is that all gases act the same. So I don't care what the substance is. Okay, if I take a balloon, it's got a certain pressure behind it, right? What happens if I breathe into it? I increase the pressure. What am I putting into it? Yes, more mass, but don't say mass.
Oxygen.
More of the.
More atoms, more molecules. I'm looking at increasing the number of things. Pressure and the number of my gas. What is my measurement unit for a number of gas particles? Moles. Volume, we could use a V. What is our symbol for moles?
M. Or M.
We might say M, except M is molarity, or meters, or milli. Let's avoid M.
MOL.
There's a reason we didn't jump straight to moles. Moles is really just a number of particles. A number of particles. And we could use N. We'll represent moles with N. What happens if I breathe more particles in?
Pressure goes up.
N goes up. What happens to the pressure?
Goes up.
It also goes up. So pressure is directly proportional to the number of particles, okay, or moles. Somebody went through and started to note all of these relationships and then noted that there were relationships between moles and volume. If I have that balloon and I breathe more particles in it, what happens to the volume of the balloon?
Increases.
It increases. I could also look at temperatures with volume and moles. So somebody sort of noticed that all these different pieces all were interconnected somehow. Okay, because of that interconnection, somebody really smart went through and put them all together in one giant mess of an equation. Okay? That giant mess of an equation is what is sometimes referred to by chemists as PIV-NERT. Why not R equals PIV over NT? How many of you like fractions? Okay, there we go. That's not a good representation, so what do? We rearrange the equation to be no fractions, and we get PIV, PV, NERT, NRT. Okay? PIV-NERT is the central equation behind it. The big thing that stands out of this is that because all of these things were related to each other, we notice that we have this R. That R is a constant. So as long as we're looking at an ideal gas, R always comes in to be the exact same thing. 0.0821 atmospheres times liters over moles times Kelvin. Okay? Why the expression? That's a lot. It would be nice if somebody, say, gave that to you on an exam. I think I'm that person. I don't remember. Okay? I should be giving to you.
Not to change. If you're not that person,
you might need to remind me. If you decide you need that on the test, you should remind me and I will give that to you. Okay? If it wasn't
need
there.
that on the test.
If it wasn't on the test already. Okay? The value behind this is I can now solve for one of those variables if I knew the other three. Okay? So this is not dimensional analysis now because we're using a very complex kind of unit conversion system that is ultimately just a formula. I'd recommend you just memorize the formula and use it. Okay? The power behind this is that we could start, to solve for some relationships. The volume of a container is doubled. Assume the temperature and the moles are not changed. What happens to the pressure? So if I increase the volume of the container, what should happen to the pressure? It should go down. How much should it go down? I don't know that. I don't have any numbers. We start with the volume of a container, conditions A. Okay? We then move to conditions B. This says the volume of the container is doubled. Do we know the volume of conditions B? It is twice the size of volume A. Okay? It says temperature and the moles are not changed, which means the temperature of A equals temperature of B. Not zero, they're the same. The moles of A equal the moles of B. And this is not an equals, this is changed to. How does this apply? If we look back up at the top, we've got an equality here, right? PAVA will equal PB VB over NBTB. Why do we know that to be true? They both equal R. And what was R? A constant. So I can set them equal to each other and kind of ignore that system. What happens with NB? What do I know NB equals? NA, which means?
Equals NB.
Those can cancel out. TA and TB? Same thing. Cancels out. What did I say VB was?
2PA.
If I want to know the pressure at B, what do I have to do?
Multiply this.
And what do I get?
PA over 3, PA over 2.
PA. What happens to pressure B? It is half the pressure that we started with. We can directly quantify it. Okay? That is the power of PV equals nRT. Okay? It requires some algebra to go in behind that. Okay? You are responsible for manipulating that. You could go through and say, well, I know it needs to go down because doubled means 2. I'm going to say it goes down by 1/2. Would you be right? Yeah. Did you have to show any work? No. Sweet. You figured it out. I don't care how you figure that out as long as you aren't cheating off somebody else. Okay? If you know those relationships, great. If you don't know those relationships, that's where PV equals nRT comes in to establish those relationships so that you can solve. That's the power of it. Yes?
Cheating off your hand count.
Yes.
Okay.
Ideal gas law problem. How many moles of neon gas occupy 2.34 liters at STP? Okay, we're going to do a race.
No.
Yep. What are you solving for? I'll set you up. Moles of neon. What are you given?
2.34 liters.
2.34, liters of neon. Are they the same thing?
No.
What do you want?
Moles.
What do you have?
Liters.
Solve. For those of you then looking at what I'm doing, you probably don't want to.
I shouldn't have looked.
Sometimes it's helpful to actually listen to the words that are coming out of my mouth. Okay, you should have solved it already, like a while ago. Because at least a couple of you have calculators, I need some help with the math here. I can't do 0.0821 times 273. That math is a little bit difficult for me to carry in my head. I do apologize. I am human. What's the number that you get?
0.021 times 273.
Yep.
22.4133. So, 366, 22.4.
What work did you guys show up here? Liters of neon should be canceled. Moles of neon should appear. Do you know a conversion factor for that?
22.4.
22.4 liters is 1 mole. When? For a gas. Is it a gas? Yes. Are we at STP?
Yes.
Can you use that conversion?
Yes.
Yes. PV equals nRT. 1 atmosphere, 2.34, N, temperature. Solve for N, plug in a bunch of stuff. 1 atmosphere, R, temperature, times the 234 liters. Set that all up right? Everybody agree? Follow all the math? What do I get? The exact same thing.
Why would you do more work though?
Why would you do more work? When are you going to be at standard temperature? Never. Having you memorize a useless piece of information is dumb. Having you manipulate PV equals nRT is actually useful because that establishes the relationship. That 1 mole equals 22.4 liters comes from the expression PV equals nRT. That's why it's there. It is only valid when at those temperatures. What happens if you tweak those temperatures? That conversion tweaks. Okay? The conversion factor you're told to memorize is a simplification of PV equals nRT. you're not doing more work. You're doing the work you should have done from the get-go instead of memorizing some stupidly moronic conversion factor. Okay? Instead of memorizing an algorithm, you should memorize the process to get there. That said, you're responsible for the algorithm in this case, not for the process. However you get there, I don't really care. Okay? Ultimately, you need to know the algorithm so you can memorize the algorithm. If you have to take more chemistry classes, freaking do PV equals nRT. It takes a little bit longer, but that's the process you're going to have to do eventually anyway. Get the practice now. Okay? Didn't quite get through all the stuff I wanted to today, which means we're going to be covering new material for the exam on Thursday on Tuesday. So you should be reviewing. You might want to go through and look at the slides that are left. We've got a little bit on gases, then it's limiting reagents, which is just more application of the stuff we've already done, and then empirical and molecular formulas, which are ultimately just algorithmic processes to solve. Okay? So make sure you review that content so it doesn't hit you as a surprise either on Tuesday or, more importantly, Thursday for the exam.